Okay, so this is the last lecture that we have on systems. We're going to finish off talking about gas turbines. Previously we had a look at practical internal combustion engines, and we compared two cycles, the Otto and the diesel cycles, because these are the most common. There are a few other cycles around, but these are the key ones for us. So gas turbines are useful for us because they make another different assumption in terms of what the heat transfer from system to environment and back again is. And the other reason that we're interested in gas turbines is we're going to have a look at these again towards the end of the module, and we'll look at them from a steady flow energy equation point of view. So this is using a finite volume, and fluid and energy is flowing through this control volume, and effectively what we'll do is we'll take a control volume for the compressor, we'll take a control volume for the combustor and a control volume for the turbine, and we'll see how energy flows through those finite volumes. So in this case we're still in the system point of view, and this is our last lecture on the system point of view. So this is a useful way of comparing the system to the control volume point of view. So we'll come back to that a little bit later. And the other thing we're going to have a look at is ways in which we can improve the thermal efficiency of a gas turbine. And there are two techniques. One is called regeneration, and one is reheating and intercooling. And certainly for stationary power systems, so these are large gas turbines that are bolted onto the ground. You might use them for power generation, you might use them for industrial compression requirements, and effectively the size and the weight of these things is not limited in the way that a jet engine is limited by weight and complexity. Okay, so we're going to have a little bit of a talk about that as well. Okay, so what does a gas turbine look like? So we are still in our system point of view, and we need to have an element of gas. So if you can imagine, we've got a little cube of gas and it's sitting at state 1. It's got to go around my cycle. So it's got to go through a compressor. So it's going to be pressurized and heated a little bit. So it's heated adiabatically here. And then it goes into a combustion chamber, and we add some fuel. We burn the fuel. We heat up our fluid, and then we take our hot pressurized fluid and we put it through a turbine, and we extract some work. And so for stationary power, our turbine has to do two things. The first thing it has to do is it has to power the compressor. So this is called back work. So some of the turbine work has to be donated to the compressor, and if you've got a correctly designed stationary gas turbine, your turbine generates some extra work, and this is the thing that you can connect up to an electricity generator or a compressor. And then once we've extracted the maximum amount of energy that we can, we have to throw our waste heat away to obey the second law, and then we go around the system again. Okay, so this is pretty much how it works, and the key point in this lecture compared to the previous lecture is that both my heating process and my heat rejection process are both constant pressure processes. So we have effectively three practical engines that we're considering in this module. We have the Otto cycle, which uses two constant volume heat transfer processes. We have the diesel engine, which uses one constant pressure and one constant volume. And we have the Brayton cycle, which uses two constant pressures. Okay, so we have different ways to transfer heat in a practical way in these three key engine cycles. So what does it look like? So on a PV diagram, we have our heat transfer processes are constant pressure. So these are horizontal lines. So this is my so 2 to 3 in this case is my combustion chamber, and this is my turbine going from 3 to 4, and then I've got my heat rejection. So I take my gas back down to ambient conditions, ambient temperature and pressure, and then I go through my my adiabatic compression to go from ambient conditions up to P2, which is the pressure at which the pressure and temperature that is the entrance to the combustion chamber. Okay, so that's pretty much what it looks like. So when we want to work out our heat addition and heat rejection processes, we are using the enthalpy change. So this is Cp delta T. So we've got both of these things here. And if we want to work out the thermal efficiency of our Brayton cycle, is what we want, which is the network divided by what we pay for, which is the heat going in. So this is the combustion energy. And when we work it out, we end up with 1 minus T4 minus T1 divided by T3 minus T2. So you'll notice that this definition of thermal efficiency for a Brayton cycle is exactly the same as the thermal efficiency for an Otto cycle. The reason is, in the Brayton cycle, our two CPs cancel to give us this equation, and in the Otto cycle, our two CVs cancel to give us the same equation. So this is not apparent because the practical way to measure thermal efficiency of a Brayton cycle is different to the practical way that you characterize thermal efficiency on an Otto cycle. And it comes down to the fact that for an Otto cycle we use the compression ratio of the engine, and the compression ratio of an engine for a gas turbine makes no sense at all. So what we do is we use the pressure ratio. So this is the pressure ratio across the compressor. So this is P1 here is my atmospheric pressure, and P2 is the compression that I've used to generate my pressurized air before it goes into the combustion chamber. So we do the similar kind of thing before. We use the gas law. P1 V1 divided by T1 is equal to P2 V2 divided by T2, and the isentropic compression relation, and we end up working out temperatures in terms of pressure ratios, and we can take this, substitute it into this equation, and we end up with the thermal efficiency of Brayton cycle that looks a bit like this. Okay, so what does the thermal efficiency look like? Well, obviously it looks exactly the same as the thermal efficiency of an Otto cycle. So all I've done here is I've reproduced that graph. So just to note, this RV is not the pressure ratio. This is still the RV of the Otto cycle, but it has the same characteristic in the sense that if you're going to run a gas turbine at very small pressure ratios, you have very bad thermal efficiencies, and the pressure ratio increases as does the thermal efficiency. So from a design point of view, the key thing that limits our thermal efficiency is the temperature coming out of the combustion chamber. Not because of what's going on in the combustion chamber, but we have to remember that the combustion gases go directly into our turbine that powers everything. So we have to make sure that our turbine blades are stable, they're not going to creep, they're not going to crack. The failure of these things, particularly in things like jet engines, is not something you'd really want to consider. Okay, so T3 is, trying to increase T3 is what companies like Rolls-Royce and General Electric spend vast amounts of money trying to get another 10k or 20k on T3. The other oddity about a gas turbine is you have to be a little bit careful about what you wish for. So if you're a gas turbine designer for a commercial aircraft, effectively what you want to be able to do is to go from A to B and burn the minimum amount of fuel. So in that case, you effectively want to have your highest thermal efficiency as possible. So that means you need to run your engine at the highest possible compression ratio. If on the other hand, you're the designer of a jet engine for a fighter pilot, effectively you don't care about thermal efficiency, you just want to get the maximum amount of work that you can get out of your particular engine. And this is typified by the figure at the top. So what we can see here are 3 engine cycles running at 3 different pressure ratios. We've got a pressure ratio of 2, pressure ratio of about 8, and a pressure ratio of about 15. And all of these engines are running between the same low temperature and high temperature limits. And you can see that depending on the pressure ratio, you get different amounts of work out of this particular engine. So if you're a fighter pilot, effectively you don't care about your efficiency and you just want to generate the most powerful engine you can. So you would design your gas turbine to have a pressure ratio of about 8. Okay, so you're going to burn lots of fuel relatively, but you'll generate the most amount of power you can with your particular piece of technology. Okay. So one of the issues with gas turbines is they're not very efficient at low pressure ratios, and one of the things we can do is to improve this efficiency by recycling some of our waste heat. So we've got our standard engine cycle here. We're going from atmospheric temperature and pressure through our compressor, through our burner section, through our turbine, and then we kind of typically we throw this energy away, and then we put in some fresh charge of air. So one thing we can do is we can say, well, we can take some of this energy from what we were going to throw away at T4, and we're going to give it to our air at T2. And if we can give some of our waste heat to the energy at T2, it means we have to burn less fuel to get the temperature to T3. So if we can have a look at this on a curve, so what we've got here is we've got atmospheric state at the start of our compressor. So we go through our compression. This is our adiabatic compression. Now if we weren't going to use any regeneration, we'd have to go from T2 all the way up to T3 by burning fuel. So we've got to go from 2 to 3 by burning all this fuel. So we've got to add energy all the way up to here, and then we do our power stroke. So our turbine extracts some energy and we end up reducing our temperature isentropically. And then if we don't use a regenerator, we have to throw all of this energy away to go from T4 all the way back down to T1, and then we go around again. So if we had a perfect heat exchanger that gave some of this waste heat to T2, then in theory what we could do is we could say, well, this is T4, so this is my turbine exit temperature, and I should be able to heat my flow going into my burner up to this 5' level. So I can go from T2 all the way up to 5' for free, because I can just recover all of my waste heat from my turbine, and I only have to burn my fuel to get from 5' all the way up to T3. Okay, so in practice, it's not economic to make a 100% perfect efficiency heat exchanger. It would have to be infinitely big, and you'd have to have perfect heat transfer surfaces, and so on and so on and so on. So typically sort of economically efficient regenerator or heat exchanger might be 70% efficient. So in that case, what that would mean is we go from 2 up to 5. So there's still a temperature difference between T4 and T5, and that's due to our inefficiency of our heat exchanger. And we have to burn the fuel to get from 5 all the way up to 3, and then we go down to 4, and then we donate some of the fuel and we throw away less. Okay, so the impact of this is very good when we get to small pressure ratios. So it doesn't have very much effect at large pressure ratios. But let's say we've got a temperature ratio between T1 and T3 of a third. So we're not doing very much compression and combustion. So we're kind of sort of down here somewhere. Now if we add regeneration, we turn this part of the curve into this bit, and we recover lots and lots of energy. So if your thermal efficiency curve with regeneration with these different temperature ratios says if you're at high pressure, you come down this curve here and you get to this point, and then you start going up here. So it's it can transform the efficiency of small gas turbines. So this, if we have a look at our regenerator, this is how you'd kind of build it. You'd have a flow diagram. So here we've got our compressor exit, T4. It's coming out here, and it goes through a heat exchanger and gets some heat from the waste of the turbine and goes into my combustion chamber. And T9 here, this is my final combustion temperature, and instead of throwing that away, I go through a heat exchanger, and some of the energy in my gas turbine exhaust gets donated to this thing here. Okay. So another way we can make our turbine more efficient is if we, instead of having one big compressor, we have a series of small ones, and we cool the gas at constant pressure. So this gives us some compression for free. If we, let's say we have we want to go from P1 to P4, and if we use a big turbine, we have to add a certain amount of work to do that compression. But if we have a staged compression, we go from P1 to P2, and let's say P2 is half of the pressure at P4. So we've done half of the compression to get us to P2, and then we extract some heat at constant pressure by passing our intercooler, our fluid through a heat exchanger, and we dump some heat. So what effectively that does is we're reducing the temperature of the gas at constant pressure. So if you think about the gas law, what we're doing is we're increasing the density of the gas. We're doing some compression for free here. And then we have our gas at the same temperature, or sorry, same pressure here, P3 as P2. And then we go through our second compression, we get up to P4, and we use less work to do that than doing the whole thing in one go. And the same thing applies for the reheater. So in this case, you've got my combustion chamber here. So effectively, I burn half my fuel in the combustion chamber, goes through first turbine, then I reheat my fuel. So I add some more the other half of my fuel, if you like, and it goes through a second turbine. And this is more efficient than having a single turbine. And the reason for this is can be explained on this figure here. So we've got a PV diagram, and let's say we want to go from P1 to P2. So this is my this is the compression ratio of my gas turbine, and let's say I want to do that with a single stage compression. So if it's a single stage compression, I have to follow an adiabatic PV curve. So that's this curve here. So if I want to do the compression to get from P1 to P2 in one go, I have to follow that S equals 0 line to go from 1 to A to C, and that gets me up to P2, and then I can give that to my heat exchanger. And if I want to use an intercooler, so let's say I've got two small turbines, two small compressors that are half as big as my big one. I go from 1 to A, and then I cool my fuel down. I cool my air down at constant pressure. So because I cool my air down at constant pressure, I reduce my specific volume. And remember, my specific volume is 1 over density. And then I do my second compression, and I go from B up to point D. Okay, and if I want to work out how much work is done to go from 1 to D, I can do the integral under this curve. So I can do the integral from 0 to 1, the integral under A to B, and the integral from B to D. And then if I wanted to compare that with the work done to go from 1 to D, I've done this amount of work, and then I've got to get from C to D. So obviously, graphically, I can see that I have to do this much extra work on a single stage compression compared to a multi-stage compression. And the same thing applies for reheating. And what does this do to my combustion cycle? So if you can imagine, I've got a single stage compression and I'm only going half of the way. So if I start off at, say, state number 3, and now I do a single compression, add my heat, do a single put it through the turbine and get back down to state 3, I enclose this much work. And if I add one extra stage, so this is a 2-stage compression, 2-stage reheater, effectively I end up doing 2 of these things, and I end up creating quite a large amount of extra area in this TS diagram. Okay, so and this is proportional to the net work that I get out of my turbine. So in theory, I could add lots and lots of these compression stages. So, but this has the inefficiency of being able to maintain it and build it, and losses and so on. So the largest gas turbines that are used in power stations, they might have 3, possibly 4 stages. And beyond 4 stages, it's not really economic. Okay, so now we've covered our final engine cycle from the system point of view. The Brayton cycle uses 2 constant pressures for the heat addition and heat rejection processes, and we've come across 2 methods to improve the efficiency. So one is regeneration, and one is to use staged compression and staged expansion. Okay, thank you very much.